vector fields. Well, what are they and what are we going to do with them? Well, so in 17.1 we were looking again at the gradient of the gradient of a function, and that outputs as a collection of vectors, and that gives us again, that stores the rates of change in the x direction and the y direction in the 2D case, of course. All right. However, back in differential geometry, which is really the topic we cover there, we took the derivative of some function to obtain the gradient. This time we're going to do the opposite to, well, yes, it's going to be some integration to obtain the function, which is called the potential function, whose derivative is that given gradient. And in fact, recall that a vector field is really the gradient of some function. All right. Well, so an overview, a quick overview of different kinds of regions. And well, this is just so you don't get freaked out when we look at some definition. Let's see a simply connected region, or not simply connected region, or closed simple, Well, so this is what these regions look like, It's closed simple, not closed yet still simple. This case is closed but not simple, and the reason, that's because we can define this as our C1 and then another C2. Two different paths. And in this case, not closed, not simple. Well, it crosses itself, so that's a C1, C2, and then C3. So we would need to parameterize this into three piecewise functions, And the same happens over surfaces here, or over areas rather than arc lengths. Well, we're going to look at these areas later when we look at the Green's theorem, which happens to deal with areas. But now, in the meantime, let's talk about conservative vector fields. A vector field F, as we have been working on, is called conservative on a region R squared or R cubed, depending on whether we're working in 2 dimensions or 3 dimensions, if there exists a differentiable scalar function phi such that F is nabla of phi. In other words, that function whose gradient is that vector field. So, and we call this phi the potential function. All right. Well, to find this potential function, we need a process, of course. All right. So number one, first we need to determine whether that potential function exists, because in some cases it may not exist. So some random gradient, some random vector field may not be some function's gradient. So, and we have to perform a test for that. And well, once we know that it exists, well, we proceed and exist. We proceed to find it. And in this case, what do we need to do to find that potential function, partial integration? Because, well, think again of some function for which we took the derivative. So, or the derivative, that is the gradient here. So from here, one thing to keep in mind is that F equals the partial derivative with respect x. G is the partial derivative of the potential function with respect y, and h is the partial derivative of the phi function, that is the potential function, with respect to z, which is simply the partial derivatives and then in angular brackets notation, right? That from a couple of chapters ago when we did the gradient. Well, so let's recall another property from partial derivatives, that is the equality between the mixed partial derivatives. You might recall that part. So whenever we find the second derivative with respect x and then with respect y, if we reverse the order, the partial derivative first with respect y and then with respect x, which, by the way, I just noticed a little typo here. y and then x. It should be yx. And well, the same with the partial derivative of x with respect z, and then with respect c, that is the same as the partial derivative with respect z and then with respect x. And the third implication here is that if we do the partial derivative with respect y, then with respect z, it's going to be the same as finding the two partial derivatives in the other order. This implies the following. So this implies that f with respect y equals to g with respect x. The partial of g with respect x. Well, how did I get that? Well, so let me take this part right here where, so this f, which is equal to the partial derivative of phi with respect x, but this one I'm going to take the second partial derivative in this case, a second partial derivative with respect to y. So this is the same as saying f with respect to y equals phi with respect x, then with respect to y. Now I'm going to take this second g equals to phi, the partial derivative of phi with respect to y, but this one I'm going to differentiate it with respect to x. This will be the partial of g with respect to x equals to the partial of phi, first with respect to y, then with respect to x. Now, did you notice something funny here? Well, phi with respect to x, then respect to y, phi with respect to y, then with respect to x. This gives rise to g with respect to x equals f with respect to y. Alright, so all we're doing is just taking second partial derivative. So I'm going to show you all these details only for this first implication. In the same way, we get the following. We get that the partial of f with respect to z equals to the partial of h with respect to x. And lastly, the partial of g with respect to z equals the partial of h with respect to y. You should get those last couple of results if you pair them again and take the derivatives with respect to another variable, the corresponding other variable. Alright? Well, so this is what we need to test when we are given a gradient or a vector field, to determine whether that vector field is some function's gradient. We need to test these three conditions right here. So let's formalize this in the next page. Alright, so we're given some f, which is a function that contains f, g, and h of x, y, and z, so that's a vector field defined on a connected, and simply connected region D of R3. So let's look at the case of R3. And well, f, g, and h have continuous first partial derivatives on D. Well, f is a conservative vector field on D if and only if these three conditions are satisfied. So when we're working with a vector field that contains the three components, we're working in 3D, yes, we have to take 6 partial derivatives and make sure these three are equal. But otherwise, if our vector field is only in R, there's a little typo here, that should be R2. We have to check only one condition, that is the partial derivative of f with respect to y is equal to the partial derivative of g with respect to x. Alright, so let's decide whether the vector field that we're given here is conservative. That is, whether this vector value function is some f of x, y's gradient. Alright, and in this case, well, number one, let's identify our f and our y. So in this case, little f equals y over x squared, and which is the same, why not, y times x to the negative 2. We may need it in this form in order to differentiate it. And also, g equals to negative 1 over x, which is negative x to the negative 1. Alright, so we just identified this f and g's. So now we need to determine whether the partial differential of f with respect to y is equal to the partial differential of g with respect x. Alright, so what's the partial derivative of f with respect to y? Is that just 1 over x squared, right? And equals, what's the derivative of g with respect to x? That's negative 1 times negative 1, and that's 1, and to the negative 1, that's also 1 over x squared, alright? That means the given vector field f is conservative, and we can find a potential function. All right. We will discuss how we find that potential function. For letter B, and it looks ugly. It has a lot of letters and exponentials here and there. But well, we need to check 3 conditions for this one. Number 1, well, let's identify f, g, and h. In this case, well, instead of rewriting them again, I'm just going to label them from here. This is f, g, and h. By the way, if you look for additional resources regarding this topic online or other textbooks use, instead of f, g, and h, they use m, n, and p. Just so you don't freak out like, hey, what's this? No, it's the same, all right? It's the same. So the number 1 condition is that we want to test is this one. F, the partial of f with respect to y should be equal to the partial of g with respect to x. So let's see if that is true. So f, okay, let me write down f sub y, that is the partial derivative of f with respect to y. So the derivative with respect to y, well, everything here is constant, that's 2x z e to the x squared y. But in this case, by mini chain rule, careful. What would be the derivative of the exponent with respect to y? X squared, right? The constant coefficient x squared. I know it looks a variable, but since this is partial differentiation, so that's 2x, and that simplifies to 4x. That's a 4x squared z e to the x squared y. Let me make it a little bigger. 4. What is that?
Partial with respect to y.
With respect to y, yes. So
X squared.
oh yeah, x squared, yeah, that's what I meant, x squared, thank you. So yeah, that's what I meant, but not what I wrote, right? So e to the x squared y, all right? So that's a partial derivative with respect y of f. Now let's find the partial derivative of g with respect x. Well, the g with respect x, notice there's x's all over the place, so in this case we need the product rule. So we need to find the derivative of the product first. Okay, the derivative of x squared z with respect x, that's going to be 2x z times e to the x squared y, plus the derivative of the exponential, which is itself e to the x squared y, by chain rule, multiply that by 2x, which is the derivative, well, 2xy, and then times the other factor, which is x squared z. And well, I think it's really easy to see that these two derivatives are not the same, right? So, since f, the partial of f with respect to y is not the same as the partial of g with respect to x, therefore f is not conservative. And therefore, this madness here, that's definitely not some function's gradient. And we are not going to be able to find the potential function. But we could for letter A. Alright. Let's see what's next over here. Okay. And I didn't type anything on the process to find the potential function. And well, so to find phi, the potential function, we will rely on partial integration. And well, what is that? Well, because for example, whenever we have, f of x, y, z, so let's call this w, f of x, w. So that means nabla of f, that's the partial derivative of f with respect to x, comma, the partial derivative with respect y, and the partial derivative of f with respect z. Alright? So that's going to give us the gradient. And in this case, this is equal to the big F of x, y, z, which is that vector field f, which is f g h. All right. So that vector field is the gradient of some function. So in this case, well, what do we need to do? So let me set these two equations together. Or actually, let me set three equations. Component-wise, setting components equal to each other. So the x component with the x component, the y component with the y component, the z.
Equal sign between the nabla f and the vector?
This one?
Or like between the two, bring equal sign?
No, this one, yeah, this one should be an arrow.
F times the vector.
Oh, it's, that should be equal, thank you. Yeah. And, oops. Z component with the z component. So, if we set these two together, well, partial f with respect x equals f. That means we retrieve the original f component of the function, like by integrating partial f equals f partial x. So just integrate both sides, and well, that's going to be f equals the integral of f. It should have been, okay, let me call this w. I think I'm having a little issue with the letters because I don't want to, no, I got it. It should be phi. Phi, which is the potential function, f dx. And in the same way for the other two components, we will have to integrate each component with respect to x, with respect to y, and with respect to z. And well, let's do one example. Even though it sounds like, oh, very straightforward, I mean, integrate with whatever variable we do. Well, there's a little downside here, and that's the part that we need to be very, very careful about how we do this partial integration. And by the way, the textbook discusses a different method than the one I'm going to do, and that's a little confusing. I'm not a big fan of it. And also, that's the method that you will see when you see the V1 example in my MATLAB. So just so when I mentioned this, so when you do the homework, you'll see something different. I think it will be more straightforward to do it this way, integrating each component and identifying what do they have in common, which you will see how it works, rather than what the textbook does, integrating one, then differentiating with respect to another variable, then setting another equation and solving here and there. I don't know, it's just confusing. So number one, let's go about one example. So let's consider this vector field f of x y equals 3x squared y squared in the direction of I plus 2x cubed y in the direction of j. Prove that this vector field is conservative and then find the potential function. Well, to prove that the vector is conservative, all we need to do is make sure that the partial derivative of f with respect to y is equal to the partial derivative of g with respect to x. So that is f sub y equals g sub x. Okay, so let's find the partial derivative of f with respect to y. So that's going to be 2 times 3, which is 6 x squared y. Do we agree? What about the derivative of g with respect to x? Again, 3 times 2, that's 6x squared times y. And yes, because these two quantities are exactly the same, then that given vector field is conservative. And therefore, we will be able to find the potential function. And we will have to do, in this case, two partial integrations. Well, because in this case, we are working in 2D, in R2 rather. We're going to denote phi of x, y, because that's the potential function, and that's going to be the integral of f dx. Well, that's the integral of 3x squared y squared dx, and the integral of this will be with respect to x, so that's a 3, or not 3 actually, x cubed y squared. However, remember when we first introduced the multiple integrals? Well, first we did these partial integrals. So technically we have to add a plus c. However, that plus c is not just a number. You might recall from that section, it is not just a number. That constant is it's a function that depends on the variable for which we didn't integrate respect to. In this case, a function of y. Alright? Let's do a second partial integration. Phi of xy equals, this time, the integral of g, this time with respect to y. Because to get the gradient, we got the second component of the gradient by taking the derivative of the function phi with respect to y. Alright? And, well, that's the integral of 2x cubed y dy, and the integral of this with respect to y, that's x cubed y squared plus c of y. Oh, c of x in this case. Because since in this case we integrated with respect to y, that constant depends on the other variable x. Alright. So to write the potential function phi of xy, we need to observe everything that we got over here. Alright, so number one, do you see the repetition x cubed y squared, x cubed y squared? Well, that's our potential function, x cubed y squared. So, here's the argument right here. So, this c of y would have been a function that just depends on y if it appeared here in the second integration with respect to y, but we didn't get such a thing. And in the same way, Here we got some potential function that depends only on x, but this could have appeared in the integration with respect x. In this simple case, we didn't get anything like that. However, you'll see what's going to happen in further examples. And another note, check this out. So that's technically the potential function. That's what the textbook does. I kind of disagree with this because since we are integrating partially and we're not integrating, we're using limits of integration, technically we should get some plus k, right? Some constant of integration, because this function, this potential function could have been, I don't know, maybe x cubed plus y squared plus 7 minus 6, you know? And it's still going to give us the same vector field. Do you guys agree with this? So, and that's the part I disagree with the textbook, not adding that plus k. So when you perform these partial integrations, don't add a plus c or a plus k, just type the function of xy, all right? Let's look at another example. So let's prove that the vector field f of xy equals 10x plus 3y in the direction of I and 3 plus 3x plus 2y in the direction of j is conservative. And if so, find the potential function. All right. So number one, identify f, identify g, and we need to prove first of all that f, the partial of f with respect to y is equal to the partial of g with respect to x. And if we show that this is true, then we can go ahead and do the partial integration. So here's the thing. Even though these functions you will get in terms of I and j, they look integrable. Yes, I agree with that. However, this cannot be just integrated if we are not sure that this vector field is conservative. All right, so what's the partial of f with respect to y? 3. What's the partial of g with respect to x? Same. Therefore, f is conservative. That means that this madness here, this vector field, is some f of x, y's gradient. And we're going to find that, well, actually we're not going to call it f because we're using f to denote the components of the vector valued function. In this case, that original function, that potential function is denoted phi of x, y. And we're going to do the first partial integration, the partial integral of f with respect x. So that's the integral of 10x plus 3y dx. And well, the derivative, the integral of 10x with respect to x isn't that 5x squared? And the integral of 3y with respect to x, that's plus 3xy. And in this case, plus some function, some c, some constant, which is a function of the other variable that we didn't take into account in the integration. In this case, a function of y. In a similar way, phi of x, y, let's do the other partial integration. That's the integral of g with respect to y. And that's the integral of 3x plus 2y dy. So that's going to be the integral of 3x, that's 3xy, plus the integral of 2y, which is y squared, and plus in this case some constant that depends on x. So here is where this c of y and c of x is going to make more sense. So notice when we integrate it with respect x first. All right, we got 5x squared plus 3xy plus some potential term that depends only on y. But do you see that this potential term that depends only on y appeared here? Likewise, on the second integration, when we integrated with respect to y, we obtained 3xy plus y squared plus some function that depends only on x. So this missing piece of information, this missing part is actually here, isn't it? So we can form the potential function by 5x squared plus 3xy plus y squared. So in other words, all we write for the potential function is whatever you see different. But for example, notice that 3xy appears twice here. Do not combine them. Do not add them. Just bring one instance of them. All right? This is actually something that you will do in differential equations when you get to exact equations. So, James, do you remember doing this with exact equations, the partial integration in something like that? Or if anyone else has taken differential equations, so that's essentially, so you are finding the integral of some total differential, which is really a vector field, and you're retrieving its solution in a similar way. All right? Okay, let's do one with 3 components. This one is going to take a good minute to go. All right, so prove that the vector field is conservative. There's no way around that. We have to do this. All right, identify F, G, and H. So, for a vector field in R3, there are 3 conditions that we need to show. All right. So number 1, those 3 conditions. Well, let me just go with them. I mean, number 1. For letter A on number 1. We need to show that f with respect to y equals to g with respect x. And I would rewrite this as a 2xy z to the negative 1 in the direction of I, or let me use component form instead. Because these quotients we may need them in a different format, so we can differentiate them. X squared z to the negative 1, comma, y minus x squared y z to the negative 2. Okay? So, the partial of f with respect to y. Well, the derivative of y in this case is just 1 times every remaining factor. That's going to be 2x over z. And the partial of g with respect x. Well, the derivative of z is going to go to 0 because that's constant with respect x. And the derivative of x squared is 2x. So that's 2x times x to the negative 1, which is over z. So far, the first condition is satisfied. There's 2 more conditions that we need to check. And that second condition is f sub c, that is the partial of f with respect to z. Is that equal to the partial of h with respect to x? Well, let's find out. That's part B. So f sub f with respect to c, okay. Negative 1 multiplying with the 2, that's going to be negative 2xy z to the negative 2 equals the partial of h. That is the third component. In this case, what do I have here? For whatever reason, I have something weird. Anyway. Well, so with respect, it's with respect x. So this term goes to 0. That's negative 2x y z to the negative 2. Does that look like the same thing? Second condition satisfied. Let's do this 1/3 time. I know it's a long process, but we want to make sure that the 3 conditions are satisfied so we can find a potential function. So the third condition is that g with respect to z equals to 1 minus, equals to h, partial of h with respect y. Alright, so let's go have a look at the function g and differentiate it with respect to z. Okay, the derivative of z here is 1. And then the derivative of z to the negative 1, that's negative x squared z to the negative 2. What about the derivative of h with respect to y? Okay, so the derivative of y, which in this case is 1, and the derivative in this case of y, it's also 1, right? Times x squared z to the negative 2. Does that look like an equality? All right. So it is conservative, okay? That means that there exists a potential function, some phi of x, y, and z's, that if you take the gradient nabla of phi, that's going to give us that vector valued function in multiple variables. All right, so let's go ahead and do the partial integrations. So phi of x, y, z. In the first case, integrate f with respect x. And in this case, well, that's the integral of 2xy over z dx. And well, the integral of 2x, isn't that x squared y over z plus some constant, right? However, this constant will depend on what? Y and z, exactly. All right, because we integrated with respect x, so this has to depend on y and z. Let's do the second partial integration. Phi of x, y, z. In this case, the integral of g with respect to y, that is the integral of z plus x squared over z with respect to y. We don't have to do any weird integration in this case because everything is x, y, and x and z. So that's just going to be y z plus x squared y over z plus some constant that depends on x and z. All right. And for the third instance, phi of x, y, z, that's the integral of h dz, and that's the integral of y minus x squared y over y, or no, over z squared. Okay, so this one we need it in this format, right? So that's x squared y z to the negative 2 dz, and we'll integrate y with respect to z. That's going to be y z, and in this case, well, minus x squared y z to the negative 2 plus 1. Isn't that negative 1 over negative 1 plus c of, in this case, x and y. Now let's clean up these negatives and the product of the negatives and the negative exponent. This will be yz plus x squared y over z. And in this case, okay, plus c of xy. So now we need to observe every single term. So check this out. So what did we get in the first integration? X squared y over z plus some potential function that depends on y and z. But do you see this function of y and z somewhere else? How about in the second integration and so in the third integration, right? Using the same argument, when we integrated with respect to y, we got whatever madness here plus some constant that depends on x and z. But did you see such a thing? Well, I'm afraid not. Let me see. No, nothing that depends only on x and z. So here is where we're going to put the parts together. So we will basically reconcile everything here and call it phi of x, the actual potential function, phi of x, y, z. All the different instances without combining, without repeating. And well, what do we have? First of all, we got some x squared y over z plus Do you see anything different? Y, Z, I think. Is there anything different besides that? That's all it is, right? Well, this is what you would plug in, or what you input in the blanks in MyMATLAB. But of course, I mean, as purists that we might be, this basically has to be some plus some constant of integration, because it's possible that it could be there. All right, and